In this video, I'm going to explain a deep result from convex geometry called the M-polar estimate. In a nutshell, this result says that every convex body can be made into a shape that's approximately like the unit ball after you apply a linear transformation to it. Now, this result involves a lot of powerful ideas, and my goal here is to just get to the heart of the matter, get to the key ideas that are the most important to prove it. So to do that, I'm going to go pretty fast, and I'll often skip details that I think you can easily fill in for yourself, perhaps with the aid of other references that are easy to find. So while you're watching this video you find any point confusing, or you feel like I've gone too fast over some detail, I encourage you to pause the video and think about what I've said and try to figure out the details for yourself. There's also a lot of beautiful theory around the ideas that I'm going to show you, and I will not dive too deep into all of that theory. My goal is just to present the minimum number of ideas needed to explain how to prove the M-polar estimate. So let's get to it. So here are a collection of bodies in Euclidean space, and the blue ones are convex. And that means that whenever you take 2 points inside one of these blue bodies and join those 2 points by a line, then the entire line is also contained within the body. Okay, so that's what it means to be convex. And if you look at these pictures, you get the sense that the blue bodies are in some sense rounder than the red bodies. They're rounder than the red bodies. And the result we're going to talk about today is about understanding how we can sort of quantify the degree to which the convexity implies roundness. Now there's a very classical result along these lines, and that's called John's theorem. I've made a video explaining John's theorem on my channel, so if you haven't heard it or seen its proof, I encourage you to check out that video as well. But here's the statement of John's theorem. It says that if you have a convex body that's symmetric, meaning that whenever x is in the body, then minus x is also in the body, then there's a linear transformation that you can apply to the body, such that after you apply the linear transformation, the unit ball is contained inside the body, and the body itself is contained in the ball of radius square root n. So in pictures, what this means is you might have a convex body that's long and skinny like this one, but then you can apply a linear transformation and make it rounder. And after you make it round, then the unit ball will fit inside the body, and the convex body will itself fit inside the unit ball of radius square root n. Okay, so that's the statement of John's theorem. It's very nice, and it's tight. So you can show that if the body is the cube, then you cannot do better than this parameter square root n here. Okay. So this is what I mean by sort of a theorem that shows that convex bodies are round, right? This sort of says that any convex body is approximately like a ball, where the approximation is in this sense. Okay. Now the M-polar estimate gives a different way to quantify the degree to which convexity implies roundness. What it says is that if you're given any symmetric convex body, then again there's a linear transformation such that after you apply the linear transformation, then if you pick a random point x from the unit sphere, the surface of the unit ball, then with high probability that point will lie inside the convex body. This corresponds to saying that the unit ball is contained inside the convex body. But now we have an error. Okay. And on the other hand, if you pick a random point on the surface of the sphere of radius log n, order log n, then with high probability that the tangent hyperplane to the ball at this point will not intersect the body. Okay, so that's what's captured here by the second condition. A random tangent hyperplane at distance order log n will not intersect the body with high probability. Okay, so this sort of corresponds to the fact that the body is contained in a ball. So the MM polar estimate is weaker in the sense that there are errors here, but it's much stronger in another sense, which is that the radius of the outer ball here is only order log n, whereas in John's theorem it's square root n. Now I want to point out that often in the literature about this subject there's a term used which is the position of the body. Okay, people might write that you can put the body in John position, and by that they just mean that there is a linear transformation that you can apply to the body. That's what it means to say that the body is in a particular position. Now I want to draw a parallel between the proof for John's theorem and the proof for the MM polar estimate that we will soon see. As I said before, I made a video for John's theorem, so you can look at the full or a lot of the details of the proof in that video. But the key idea to prove John's theorem is to use the ellipsoid of maximum volume that's contained within the body. So to prove John's theorem, you first find the ellipsoid of maximum volume that's contained inside the body, and then you choose a linear transformation to be the unique linear transformation that makes that, or to be a linear transformation that makes that ellipsoid be the unit ball. Okay, this is the linear transformation that you pick. And for the MM polar estimate, the idea is very similar. Again, it's based on finding a nice ellipsoid. What we'll do is find the ellipsoid of maximum volume that in a certain approximate sense is contained within the body. Okay. So the set of feasible ellipsoids here will be slightly different, but we'll again look for the largest one. And then again, we'll pick the linear transformation that makes that ellipsoid equal to the unit ball. Okay. So that's the idea. Now, in order to state what I'll actually prove, I need a couple more concepts. It turns out that every symmetric convex body is associated with a norm, and the body and the norm are more or less equivalent. Okay, so given a symmetric convex body K, you can define a norm like this. Let alpha be the minimum non-negative number such that x divided by alpha belongs to K, and this alpha is the norm of x. Okay. Now, given any norm, you can also obtain a symmetric convex body by taking the unit ball of that norm. And then there's a second norm that's associated with the body that's called the dual norm, and the dual norm of x is just the maximum value of the inner product that x can take with any point inside the convex body. Okay. So those are two useful concepts, and they basically allow you to measure sort of how far a point is from the body. And once we have these concepts, we can state a theorem that captures the MM polar estimate. The theorem says that given any symmetric convex body K, you can put it into a position, namely you can apply a linear transformation to it, so that after you apply that transformation, the norm and the dual norm satisfy this inequality. The inequality says that if you, for x that's a random point on the sphere of radius 1, the expected value of the square of the norm of x, and the square root of that expectation, times the same quantity for the dual norm is bounded by order log n. Okay. Now I'll leave it to you to verify that this type of statement implies what I claimed earlier, which is that there is a position that you can put the body in such that after you put the body in that position, then if x is a random point on the surface of the sphere of radius 1, then with high probability x is contained inside the body. And if you pick a random tangent hyperplane to the sphere of radius order log n, then with high probability this hyperplane does not cut the body. Okay. So theorem 1 implies those two facts in a somewhat straightforward way. Now, in this video, I'm not actually going to give all the details for theorem 1. I'll instead prove theorem 2, which is very similar because theorem 2 actually involves most of the ideas. Theorem 2 is very similar to theorem 1, but there are a couple of differences. One difference is that I've replaced the unit sphere here with the Boolean cube. Okay, so instead of taking points x from the sphere, I'm taking points x from plus or minus 1 to n. And to compensate for this, the bound has an extra n, okay, because the cube is bigger. Okay. And another difference is that I'm going to apply the linear transformation to the points rather than to the body. Okay. This will make it easier to prove. Now let me justify both of these changes. The first observation is that given any point x, saying that x over alpha belongs to L of k is equivalent to stating that L inverse of x divided by alpha belongs to k. These two are equivalent. And that sort of justifies why this quantity is similar to this quantity. And similarly, the maximum of over y in L of k of x transpose y is equal to the maximum y in k of x transpose L y. But that's equal to the maximum value y in k of L transpose x, the whole transpose, times y. And that justifies why this sort of corresponds to this. Okay. Now finally, I need to explain why it's okay to replace the sphere with a cube. And basically, that's because of the central limit theorem. Given any convex body k, as in this theorem statement, I can generate a convex body k prime, which I'll think of as a convex set of matrices with dimensions little n by capital N. And what is k prime? I'll say that x is in k prime if and only if x times all 1's vector divided by square root of little n times squared n times big N belongs to k. Okay. So this defines a convex body k prime. And the point of this is that now if you take a uniformly random matrix X here with plus or minus 1 entries, you apply this transformation to it, the vector that you get here is going to be distributed very close to a Gaussian, okay, by the central limit theorem. I've set up these parameters so that this vector looks like a Gaussian, and Gaussians sample very close to the surface of the sphere. So I claim that if you can prove theorem 2 for this body, this convex body, then that more or less implies theorem 1 for this convex body. And again, I'll leave it to you to verify the details. Okay. All right, so now we're getting closer to the heart of the matter. We only need to prove theorem 2, and that's what we'll do. To prove the theorem, we're going to use a really beautiful inequality from Fourier analysis called Pajor's inequality. I'm not going to prove Pajor's inequality, but I might make a video at some other point giving a proof of Pajor's inequality. But for now, I'll just state it. So first, let me recall some basic facts from Fourier analysis. Given any function h that maps the cube to vectors, you can always write h of x as defined using polynomials in this way. You can write h of x as a sum like this, where every one of these coefficients is a vector living in the space R to the m. Okay, that's a standard fact that I'll leave it to you to check. Now, maybe an observation is that this is basically you're allowed to write here any polynomial. The point is that it never makes sense to square a variable because the inputs come from plus or minus 1. So the square of any variable is equal to 1. So that's why all the monomials have all the variables in the monomials have degree at most 1. Okay. So every such function can be expressed as a polynomial. And moreover, once you have this, given two functions like this, the expected value over x of the inner product of h of x times g of x is equal to the inner product of the corresponding coefficients. And that's because when you take this expectation here, only the expectation of every variable xi is 0. So only these cross terms survive the expectation. All other terms contribute 0 in the expectation. Okay. So in particular, this means that whenever you have an expectation like this, if, for example, g is a linear function of x, then only the linear coefficients, only the degree 1 coefficients of h matter. Okay, only the linear coefficients of h contribute anything. All right, now let's state Pajor's inequality. Pajor's inequality says that if you have an arbitrary function h like this, and you just take the linear part of it, okay, the linear part of it corresponds to some matrix, which I'll call capital H. Then the expected value of h of x squared, the whole thing, the square root. So if you just take the linear part of this norm applied to h, then it's bounded by log n times the entire the norm of h of x. So dropping the higher order terms can only increase the norm by a factor of order log n. Okay, so that's a very powerful inequality, and we'll use it to prove the theorem that I stated earlier. Now, as I said, we're going to prove the theorem by considering an ellipsoid. So let me just recall some basic facts about ellipsoids. You can think of an ellipsoid as the result of applying a linear transformation to the unit ball. Okay, so say you start with a unit ball and then you apply a linear transformation, you'll obtain an ellipsoid. Okay. The volume of the ellipsoid is then proportional to the determinant of the matrix that corresponds to the linear transformation. Okay, and it turns out you can also show that it's no loss of generality to assume that the linear transformation is symmetric, although I don't think we need this in the rest of the proof. Okay, so that's what an ellipsoid is. It's just the image of the unit ball under a linear transformation, and its volume is proportional to its to the determinant of the linear transformation. So now we want to prove this theorem, and here's how we'll prove it. We're going to choose L. We're going to find that, consider all the linear transformations L such that this quantity is at most 1. Now this quantity corresponds to applying a linear transformation to this corresponds to finding the ellipsoids that are approximately contained within the convex body. That this is sort of a quantitative sense in which the ellipsoid is approximately contained inside the convex body. And among all such ellipsoids, we're going to find the ellipsoid with the largest volume. Okay, so for every choice of L inverse, we obtain an ellipsoid. We'll take the one with the largest volume. Okay, so this is exactly the outline of how we'd found the linear transformation that I promised a few minutes ago. And now my goal, so by the choice of L inverse here, the first quantity has already been set to be at most 1. So my goal is to show that the second quantity here is bounded by n log n. So that's what we'll do. All right, so we have an L that's chosen, matrix L chosen this way, and we need to bound this quantity. So let's do it. Let's write the expected value of x, the norm of L transpose x, the dual norm squared, and let's work with this quantity. The first thing I want to observe is that you can express this as an inner product. You can write this as L transpose x transpose times h of x for a function h that I will now define. Now, by the definition of the dual norm, there is a vector y in the convex body, k, such that the dual norm of L transpose x is equal to the inner product of L transpose x with y. So let's set h of x to be equal to the norm of L transpose x, the dual norm of L transpose x times y. Okay. Then you see that the inner product here is equal to the square of the dual norm. Okay. But we already observed that if you're taking the inner product of a linear function with something that's nonlinear, then only the linear part contributes. And that means you can write this as the expectation over x of L transpose x, the whole transpose, times h times x, where this matrix H corresponds to the linear part of the function h of x. Okay. Now, what's written here is a quadratic form. It's a quadratic form. Let me write it out explicitly. So it's the sum over all ij of LHIJ times xi times xj. But whenever I is not equal to j, the expected value of xi times xj is 0. So the only terms that contribute here are the diagonal terms, and this quantity is equal to the trace of L times h. Okay. So that's what we need to bound. Now, up to this point, I haven't used the choice of L, really. And now we'll use the fact that the L is the maximizer here to bound the trace of L times h. So let's do that next. To bound the trace, I'm going to use a particular determinant. Let's consider the determinant of L times L inverse plus epsilon h divided by beta, where here I'll set beta to be equal to the expected value for x from the cube of the norm of L inverse plus epsilon h times x squared to the power 1/2. Okay. In other words, this is just the norm. Beta is just the norm of this matrix according to this norm. Okay, so this is, you can think of it as a normalization of the matrix. Now this is equal to the determinant of L times the determinant of the normalized matrix. But because this matrix is a valid candidate here, its determinant has to be bounded by L inverse. Okay, so this is at most determinant of L times the determinant of L inverse, which is equal to 1. That's on the one hand. On the other hand, just multiplying this out, what's written here is the determinant of the identity plus epsilon LH divided by beta to the power n. Okay. And now let's bound beta. Beta I can bound using the triangle inequality. It's the expected value over x of L inverse x plus epsilon norm of hx, the whole squared to the square root. This is by the triangle inequality. And applying again the triangle inequality again for the Euclidean norm, I can bound this by the expected value over x of L inverse x squared plus epsilon times the expected value over x of the norm of h of x, h times x squared. All right. Now, by the choice of L inverse, this first quantity is at most 1. Okay, so I can just replace it with 1. That's an upper bound on beta. Okay, so let's look at what we've written here. At the very top here is a ratio. It's at most 1, but the numerator looks like 1 plus epsilon times the trace of LH plus some epsilon squared terms, and the denominator looks like 1 plus epsilon times expected value over x of the norm of h times x squared 1/2, the whole to the power n. Okay. And so the denominator, the coefficient of the denominator here, the coefficient of epsilon in the denominator here is just n times this. Okay, so what's written in the denominator here is really 1 plus epsilon times n, this quantity times n plus some epsilon squared terms. Okay, and that means it has to be the case, this whole quantity here is bounded by 1. So it has to be the case that the trace here has to be smaller than this number. Otherwise, for a very small epsilon, you'll get a quantity that's larger than 1. Okay, so the upshot of this calculation is that we can bound the trace by n times the expectation over x of the norm of h times x squared power 1/2. And now we apply Pajor's inequality. So by Pajor's inequality, this is at most order n log n times expectation over x of the norm of h of x squared to the power 1/2. But what is the norm of h of x? The norm of y here is 1, okay, because y belongs to the body. And so the norm of h of x is actually equal to the dual norm of L transpose x. And this proves exactly what we wanted to prove, because here you have this quantity, and here you have its square. So dividing it out, you get what we wanted to prove. So I'll stop there, and I hope you enjoyed the proof.